Hello everybody, and thank you very much for taking the time to join our session, our webinar today. We are going to discuss about how to optimize the performance of Infinet wireless point-to-multipoint sectors in case of using TDMA software-based or polling software-based. In the agenda today we are going to have a TDMA overview. Then we are going to discuss about the synchronization mechanism. Then we are going to have an overview on polling mechanism, and of course some comparison between polling and TDMA. And in the end of the webinar, we are going to take some conclusions out of the two options that we provide today. First of all, TDMA stands for time division multiple access, and its main purpose is to control the access to the shared medium by assigning different time separated channels for each user. And in a point-to-multipoint scenario where multiple CPEs are connected to the base station in a sector, TDMA allocates a fixed time frame for each CPE based on a specific algorithm. Let's now see how the TDMA frame looks like. This is a general picture where we summarize the main aspects for this TDMA frame in order to have an idea, a big picture about how it looks like. We can compare a 5 milliseconds time frame with a 2.5 milliseconds frame, and we can notice that the frame is divided into the uplink slot and the downlink slot. The percentage allocated for each direction can be, of course, customized to fit with the demands of the actual traffic. And we will see more details about this later when discussing about the practical implementations. The synchronization field for the TDMA header contains control information that facilitates the synchronization between the base station and the CPEs. It also contains acknowledgements for the data chunks and the schedule algorithm that instructs the time frame allocated for each CPE. The sync field has, and this is very important, has a fixed duration for a given bandwidth, and it does not depend on the time frame duration. Also, we have guard interval that is introduced in order to take into account the time that it takes for the farthest CPE to reach the base station, and in this case to prevent the base station from switching to transmission before the last frame to be received. For longer distances, the guard interval will be larger, and we need to wait around 3 microseconds for each kilometer. Total amount of overhead, which is composed from the sync and guard information, is approximately constant for a given bandwidth, and the maximum distance, it does not depend on the airframe duration. And for this reason, it can be seen that reducing the time frame from 5 milliseconds to 2.5 milliseconds significantly decreases the amount of useful data that can be transmitted in the time frame. The capacity is less than twice reduced in this case, and on the other hand, of course, the advantage is that latency is reduced to a half. Also, we have to consider an example that will show us how the frame processing is performed in order to better understand the concept. When the CPE receives the Ethernet frame, it will compress by stripping the unnecessary information from the header, and will transform it into a mint frame by adding the mint header. In TDMA, the frames are then divided into time chunks with byte precision in order to best fit the fixed transmission frame. And this is the key differentiation between the polling, which we are going to discuss in a few more slides, and the TDMA. And I repeat this information that the first part is mint frame 1, which is encapsulated by a TDMA header, and also the guard interval, which is added further. The TDMA frame is then sent to the radio module that will prepare for sending it over the air. And what is left from mint frame 1, because we discuss about fixed frame duration, so of course we have all the time some bytes that will not fit in the actual frame. They will be left for the next frame. Further, we have a short review about what we have to configure into the software in order to set the frame duration. Actually, it's a very simple action that we have to do. First, we have to run the TDMA firmware, and as you know, by default, we have the unit running the polling software. We need to upgrade the software to the TDMA, and for the master unit, we need to configure the frame size, which is a parameter that has the values from 1 to 10 milliseconds. Of course, we have other parameters here to set, like downlink coupling ratio, specifying the percentage of allocated bandwidth between the uplink and downlink. This can vary between 20% and 80%. And if the downlink uplink ratio is set to 0, flexible management is permitted based on the predominance of the traffic in one direction. The max distance specifies the range of the sector in kilometers. It gives us the propagation time to reach the farthest CPs and helps to reduce the guard interval duration. As a recommendation, advise to set this distance with 3 to 5 kilometers more than the actual distance, than the real distance in the field. And in case of non-line of sight or in the presence of reflections, it requires like 10 or 20 kilometers more than the real distance. Also, it provides better resilience against multipath propagation and better operation in long line of sight scenarios. Another parameter that we have to set is the RSSI, the received signal strength indication, which sets the maximum level of the input signal to which the sector has to hear the CPs. And in this case, each client device will automatically self-adjust its transmit power to not exceed the limit. About synchronization, and as I said, we need to have the version upgraded to TDMA from polling, which is by default. Then we have to do the settings according to the parameters that we have discussed, which are available in the TDMA software. And since every data transmission must occur at a precise allocated time slot, time synchronization is essential in the TDMA. Two aspects we need to consider here. First, the synchronization between the subscriber units and the base station. And in this picture, we can see how the base station and the CPs switch simultaneously between transmission and reception. This prevents CPs from interfering with each other when communicating with the base station. The CPs are synchronized by the base station, and the base station sends them the timing information in the sync header. If you deploy a standalone point-to-multipoint sector, the base station can use an internal clock generator also and can synchronize all the CPs to it. However, if you have collocated base stations, this introduces a new synchronization aspect, because when we collocate more base stations into one fixed location, and of course in case we don't have a distance separation between the base stations, then it's mandatory to connect these base stations to our GPS synchronization module in order to synchronize them and to set the same timing reference for all the base stations. In this scenario, when we discuss about collocating base stations, if the base stations are all synchronized using a common external clock reference like GPS, they will all switch between transmission and reception in the same time. We can see also in this animation. And it is important to mention that the frame size and its uplink-downlink separation should be set to the same values on the synchronized sector base station. Another important remark about chart the units that we allow to use the synchronization hub, because here we discuss about some physical connections between the base stations and the hub using the serial cables. Actually, only the hardware revision 8 from R5000 series can use the external synchronization hub. Our synchronization hub has a built-in GPS antenna and also the GPS set in order to receive the time clock. Having this synchronization deployment, this minimizes the inter-base station interferences related to hardware 11 revision. In case it is used for a base station, we only can rely on its internal clock generator that will be the source of synchronization for the CPs. So in this case, the base station will be able to synchronize only its own subscribers, but it will not allow synchronization with other base stations. We will see a bit later what can we do in order to address also this case. The synchronization hub has some important features like GPS or GLONASS receiver. As I said, it has an active antenna, GPS antenna. Geopositioning information and the UTC time is derived from the GPS signals, so it can provide GNSS base timing reference. Time synchronization is also ensured with an accuracy of less than a microsecond. preventing the interferences between co-located base stations, and in our case we discuss about up to 7 base stations. Also the console port is present only in, as I said, H08 hardware revision, is used for receiving the clock source from the synchronization hub. The synchronization information that the base station receives from the hub are just power impulses. It's just a very small amount of information that the base station receives from the hub in order to set the clock. Now we need to have an overview also on the polling software version, which is running by default. In general, polling is also a medium access control mechanism that it is based on the transmission of the authorization markers, which are sent by the master unit to the slave units. There are some highlights that also should be kept in mind for polling, like the following. The transmission frame is no longer fixed. So here we discuss about a completely dynamic and adaptive system. Polling sends the entire Ethernet frame of a variable size. Polling improves the stability and throughput by allowing access to the CPEs, by analyzing their transmission load and the link quality also. Polling can also prioritize the heavy load CPEs in order to avoid congestion, and it can distinguish the CPEs that have low transmission rate. Therefore, it knows how to efficiently send the authorization markers to allow the transmission to the CPEs. However, when the low-speed CPEs get to send their data, the other CPEs have to wait for the whole frame to be sent. As I said, polling is dynamic. It does not waste resources. Only the CPEs that have data to send will be polled, and both uplink and downlink directions are used according to the actual load. Further, a CPE will send a whole frame, and after that the channel can be used by another unit. It is particularly very useful when the CPEs does not have direct visibility to the base station, so they cannot hear each other in order to avoid collisions when the standard CSMA collision avoidance wireless access method is used. And in case of polling, the transmission of the CPEs is always controlled, of course, by base station. And another important information is that the polling can also takes into account the QoS. So not only the quantity of the data is important, but also the quality of data that the CPEs has to transmit. So priority traffic is favored compared to the best effort traffic, avoiding priority packets to be lost. In this case, delay and jitter are also optimized, and this is very important for sensitive applications like voice, video, and so on. Also, polling can be enabled from the link settings section of the master unit, and this is just a very easy setting that we can do. And as you can see, we have 3 options. We have the option to disable polling, to enable it, or to enable QoS polling. Example, the next example, we illustrate the main functionality of polling, which means that the base station polls for requests in a specific window, and it waits for the CPEs that have data to send to respond with a reservation request. Then the base station takes the decision which CPE should transmit its data on load, link quality, and other factors. These are the main criteria. And in our example, in this slide, it sends the authorization marker to the CPE2 first, and then to the CPE1. So CPE2 will begin transmitting its frame, and afterwards the base station polls the CPE1, informing that it is allowed to send its data. CPE1 send its frames, and in this example we see how the base station transmits some data in the downlink as well, for which it does not need marker access. Let's see how frame processing is performed when polling is in use. We'll assume CP1 has data to send, and it is polled by the base station. Then the Ethernet frame is compressed by stripping the unnecessary information contained into the protocol headers, and it is converted then into a mint frame. Mint adds its own header in order to be able to route the packet through the Mint network. Afterwards, standard 802.11 encapsulation is performed, and the whole frame is sent over the air. Of course, for the next CPE, which is polled further by the base station, we have the same mechanism. In our example, the Ethernet frame that needs to be transmitted by the CPE2 is larger, emphasize the fact that that polling is dynamic and does not work with fixed frame length. Of course, even in the situation that the frame is larger for the CPE2 in this example, it will be entirely sent and not trunk like in TDMA. The process is the same, then mint encapsulation is followed by 802.11 encapsulation, and then it will be sent through the air. Because of the long radio headers and the wasted time for acknowledgements of single frames, the concept of aggregated frames was of course introduced, and several Ethernet frames are aggregated and transmitted in a row using a single radio header, and a single block acknowledgement will be sent to the air. And now let's have a look to some practical considerations using using either polling or TDMA. First of all is frequency reuse. The biggest advantage when using the synchronization hub with the TDMA software is the possibility to reuse the frequencies for the collocated unit. In general, the base stations are installed closer to each other on the same mast and back-to-back. So in this case, if they are not synchronized, the base stations will interfere with each other because they hear the neighboring sector much better than they hear the weaker signals coming from their own CPEs. Now we'll consider an example to see how frequency allocation is performed in the case of 4 collocated base stations mounted back-to-back. The first allocation method that we see is the above system, above reuse scheme. This can be implemented for synchronized base stations using an external hub. And in this case, the 2 channels F1 and F2 are adjacent, and they are only separated by 5 megahertz because sectors are synchronized, because again we have in this case synchronization performed. Now considering 20 megahertz bandwidth for each channel, we need a total of 45 megahertz in order to plan the frequencies for all 4 sector or collocated base stations. In the second case, we will check the frequency allocation when polling is used or when external synchronization is not available for TDMA. In the back-to-back configuration, the frequencies cannot be reused by any means, and we need in this case, 4 different frequencies from the start, and the base stations transmit at different moments. They will interfere with each other, definitely, through both back lobe and main lobes. And in this case, at least 20 megahertz separation should be considered between each channel, and I must say that this is the minimum. I mean, it should be in some situations more than 1 channel separation between them. And if we make a calculation, we get a total of 140 megahertz. That is a very large amount of resources that we need, frequency resources that we need, comparing with the 45 megahertz we have for the previous case. So spending 140, as in this example, for the collocated base station can be inefficient in some situations. We have to use, of course, other methods that will allow us to reuse the frequencies, like in the case of the above system. And we have to consider distance separation is one of the best options, or by either mounting antennas at different heights, so vertical separation, but again a distance separation between them, or mounting the units on different poles in order to avoid these interferences. Now let's have a discussion about the number of subscribers units, because it was a very often question that that I received in the training sessions. So in case of TDMA, the increasing number of CPEs means significantly increasing the latency. This is the major disadvantage here. And roughly speaking, the delay is the number of CPEs times the duration of the TDMA frame when subslots are not used. And additionally, if several CPEs have no data to send, they still get their turn for using the fixed allocated slot, so the capacity is wasted. And it is recommended to divide the TDMA frame into subslots for larger number of CPEs. In case of range now, there is no preferred choice between TDMA and polling, so however, some aspects can be mentioned for each case. like longer distances in TDMA means larger guard intervals, and therefore it decreases the actual throughput. For long links, increased frame size are more helpful. However, if a subscriber unit is far away from the base station and has lower signal to noise ratio, this will not affect the other CPEs because it will uses only his time slots to send with lower speed and retransmissions if necessary. The other CPEs will send their data faster in their own allocated time slot. In case of polling, when a subscriber is far away from the base station and it has a bad radio conditions, the drawback is that the other units have to wait for the CPE to finish the whole frame transmission at lower speed. TDMA has more stable performance in case of non-line of sight, as well as in the presence of multipath fading, like for example links over the water or multiple reflections. The fixed transmission intervals and the guard interval makes it easy to determine the useful signal and wait until the multipath components vanish before switching between the RX and D. Another aspect is throughput versus network performance. And since the TDMA frame is fixed, we need to avoid situations when there is not enough data to fill the frame because in this case we have capacity wasted. This makes one thing of using the shorter frame size, which solves this problem but decreases the actual throughput. On the other hand, if we need more capacity in case there is a lot of data to send, one will think that using long time frames this increases, of course, latency, but of course we always have to bear in mind that the balance between the network performance and throughput is required in case of TDMA. In TDMA, if a CPE has nothing to send or cannot fill the entire TDMA frame, it still has a fixed allocated time slot. However, in polling, only the CPEs that have data to transmit are given permission to send, to transmit. Also, the load of the CPEs in case of polling, it is taken into account, as I said before, and these aspects of polling improve the throughput and the efficiency in conditions of heavy load. Concerning the network quality, polling is characterized by lower latency compared to TDMA. However, for long packets and when the traffic volume is increasing, the delay will also increase. The need to listen to the medium for the authorization markers introduces additional delay with values that vary randomly in wide limits, particularly in presence of noise. This leads to an increase of jitter, of course, which is the deviation from the average delay of the packet. Jitter is therefore random and can vary in large limits. However, in polling QoS, we can ensure better delay and jitter values for sensitive applications. In TDMA, jitter is very stable since the transmission slots are fixed. Let's have some consideration about the TDMA subslots and the downlink-uplink ratio practical considerations in the TDMA implementation. In order to reduce the delay and increase the overall efficiency of the system, the TDMA frame can be divided into subslots for each direction. We can see in this picture how a 5 millisecond frame is divided into 2 downlink slots and 3 uplink slots, each slot being allocated to different subscriber units. The delay in uplink will be 3 times lower and in downlink 2 times lower. The subslot division is recommended when a large number of CPEs are linked to the base station. Also, it is recommended to use subslots in case of delay-sensitive applications like voice. And for example, dividing the frame into 2 subslots for each direction will decrease the latency to half, in the detriment of about 8 to 10% reduction of the actual throughput because of the intra-slot guard intervals that need to be added more. But since the voice packets are small, the subslot division will only impact positively. However, the more subslots are used, the smaller is the proportion of the payload data and the larger are the overheads. This is especially determined by the uplink direction where the headers serving the traffic are larger. Therefore, in order to obtain the symmetric load of the sector, the downlink uplink ratio should be smaller, for example, 40%. When the uplink traffic is predominant, such as CCTV, the downlink uplink ratio can be safely reduced to a minimum, creating a maximum number of uplink subslots to decrease the latency. And in the last part of our webinar today, we have a comparison between the TDMA-based software and the polling-based software, which summarize the advantages and disadvantages of each firmware. We have smaller jitter in TDMA, but in polling we have lower latency for prioritized traffic. In TDMA we can have adjustable but fixed uplink downlink ratio. In polling we can do the same but using a workaround, using the traffic shaping feature. By default, uplink and downlink are dynamically according to the data load, to the requested data per each direction. The number of the CPEs in the TDMA can be up to 32 in 20 megahertz and a bit more in 40 megahertz. In polling, we can discuss about more than 100 CPs. So in case of polling, we don't have such. Also in the TDMA, we don't have a fixed limitation, but it's just a matter of performance. Thank you very much, and I wish you a pleasant day ahead.